CCNA1 Chapter 8 IP addressing. Finally, we get to the fun stuff. The network layer addressing addresses, right? Network layer address. Anyways, IP addressing, right? The logical addressing. So what we're going to do after this is describe the structure of IP version 4 addresses, describe the purpose of the subnet, compare the characteristics and uses of unicast, broadcast, multicast, and compare the use of public address space and private. Explain the need for IP version 6, and explain all the same stuff with IP version 6. And then finally, describe the role of ICMP in an IP network. ICMP, it's a little different in IP version 6 than IP version 4, but mostly we use ICMP. We use ping or traceroute. Those are ICMP protocols, and so that's what we're going to do. I'm going to skip the Internet of Everything, and we're going to go straight to IP versions 4 structure, right? So IP addresses, hopefully you know, are in binary. And so let's talk about computers use SCSI, or ASCII, sorry, ASCII, not SCSI, ASCII. Anyways, if you want to play around with ASCII, that's how they interpret things. But IP version 4 addresses are in dotted decimal, right? So each one has 8 bits, which is an octet, right? So these are octets. And so dotted decimal is then converted into binary, and the whole thing can be 32 bits, right? Because of 8, 8, 8, 8, 32 bits. Okay, so dotted decimal is where we take binary. This is the binary for 192. It's right there. Binary for 168, right there. Binary for 10, right there. Binary for that 10, right there. Notice they're the same. Okay, so how do we get this? Well, we've kind of gone over this in class, but basically so this is one octet broken down. So the 7th bit, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, and I apologize, they're not the same size. So the first bit is 128, right, if we have one there. Because we've gone over this before, 2 to the power of 7, which, remember, this is not the binary value, right? The binary value is 2 to the power of 8. If we had all 8 of these, or all 8 of these, each one is 2 to the power, starts out with 2 to the power of 1, unless we're converting them into decimal, then it starts out with 2 to the power of 0, right? So all this added up, what it can add up to in decimal is 255 if we had all ones, right? If we had all zeros, it'd be 0. So there's 8 of these, so 2 to the power of 8 is 256. So why 256? Because we have 256 usable addresses inside of there, 0 to 200. Oops. Alright, so we have 256 usable, but it's 0 to 255, which is 256 digits, right? Alright, so hopefully that makes sense. If not, alright, so how they're getting 192, they have 2 ones, the rest of these are zeros, and let's say if we had a 1 there, it actually would be, then we have a 64, so we have a 128, a 64, and a 1. Actually, that's a 2, so we're just going to go with it. That's a 2, because the value is 2 right there. So we'd have 194. That would make up 194. But anyways, each one of these, as you can see, first digit is where the 128. Next one, 64, 32, 16, 8, 4, 2, 1. Now remember, that's just, this is what the decimal conversion from binary is 128 if it's in the 8th octet bit, right? It's not it is the 8th binary digit, anyways. So just more on this. Let's see what they have here. Just more on converting binary addresses to decimal. Most of you guys are pretty good at that, right? We're just going to add these up. That's all. So all we're going to do is take this, right? Every time these octets, the digit in that column is worth this value. So all we have to do is, if we're breaking it into something, say we had an address of 200, we would just say, hey, does it go into 128? And it does, right? So we have one digit. So 128 minus 200 is, I believe, 62. Nope, it's 72. 72. Bad math. Sorry. 72. So then we have does 72 go into 64? It does. 70. We have 8 left over if we minus 72 by 64. So our next digit is 32. It does not go into 32, right? It does not go into 16. That'd be our next one, as you guys see. So we went to 128, 64, 32, 16. But it goes into 8. Okay, and then we have 0 left over, so we have all zeros. And remember, there's going to be 8 because these are octets. So we have 1, 2, 3, 4, 5, 6, 7, and 8, and those are zeros. So anyhow, that's what we're getting there. Hopefully that's making sense. If not, read that activity. Definitely do this activity binary to decimal, and I would work on this anytime you could, because when we do subnetting, which will be the next chapter, I believe, or the chapter after that, it's where we take the subnet, we make different networks, and there's lots and lots of subnetting on the CCNA certification. So you want to be able to do it with one hand behind your back. I guess that'll make it harder. So converting decimal to binary, that's what I just did for you guys. And as you can see, it's just subtraction. So I already did that where we were converting binary to decimal. I did the opposite already, but if you don't get that, here's what we do. But like I said, we have 168. Does it go into 128? Yep. We have 40 left over. Okay, does 40 go into 64? No, it doesn't, so we put a 0. Does 40 go into 32? Yes, it does, so we put a 1. We get an 8. Does it go into 8? It does. Or does it go into 16? It does go into 8, and the rest are zeros because we have 0. Okay, so that's how we do that. So converting decimal to binary, 192, same deal. I don't know. You guys can look at this again. It's just subtraction, so hopefully it's not that hard for you. Binary activity, binary game. Yeah, do that. Get that. Do it when you can. It's going to make all this math so much easier if you can just do it as if it was normal addition or subtraction. Okay, so now we have the subnet mask. And so in subnets we have 2 types of bits. We actually have more, but right now we just have 2 types of bits. 1s and 0s. So 1 is a network bit. And what that means is where the 1s are, shows where our network portion of our addressing scheme is. So remember, the network is, it's like, okay, so in this building is an IP network, and so this building has a name, and we're going to call it, I don't know, if we're dealing with LCSE, we'd say, I don't know, Clark Hall. Alright, so there's Clark Hall. That's the same thing as it says, alright, this is 192.168.10.0. That's the name, right? So that's that. Then inside the building, there's a bunch of rooms, okay? And so each host is a usable room, okay? So Clark isn't a usable room. It's just an indicator. So in every network, we have the network address we can't use. Can't use this, right? Well, we can use the 10 portion, sorry. We can't use 192.168.10, all right? And then we can't use the broadcast, which is the last on the hosts. Last host address. Alright, so the network is the first host address. or the first address, not the first usable, but the first address. And the broadcast is the last, and a broadcast just sends traffic to every host on the network. So if I sent it to, if I wanted to beam a message to everyone in our old Clark building drawing, I would send it to the last address, which in this one is 192.168.10.255.255. Alright, because, and now how do I find that? Well, these host bits tell me how many hosts I have. And there's 8 host bits, so 2 to the power of 8 equals 256. Okay, so these ones are network bits, tell us where the network is, like this. And then anything that ends on a 0 is then, well, I guess not anything, because our broadcast will, but then our host bits just tell us how big our network is, right? So if I had another 0 here, then I'd have 2 to the power of 9, which equals 512. Now remember, how many usable hosts do I have? Well, I have to subtract my network, the first unusable, and my last, so I have to minus by 2. So there's actually 510 assignable, right? So I could have 510 computers on a network that has 9 host bits. I can have 254 on this one, on the 255.255.0, also known as /24. And so how do we get that prefix, the /24? It's because 255 is 8 ones, 255 is 16 ones, 255 is 24 ones. If I had one more 1, like say if this was a 1, now this is a 1 again, if this was a 1, I'd have a /25, and this subnet would actually be 8128. And hopefully you see that, because this one equals 128. Alright, so if this is a 1, then instead of this equaling 0, it equals 128. Now another thing about these subnets, okay, they have to be consecutive ones. We can't have a 0 right here. If we have a 0 here, all the rest of it is 0. So they have to be consecutive ones. Okay, so we can only have so many numbers as a subnet mask. We can have 0. We can have 128. We can have, I'll bring this over here so we can, so our subnets that we can have 0, 128, 192, 224, 240, 248, 252, 254, and 255. Alright, and why we can have those is because we have 8 zeros. So it's 8. 1, 2, 3, 4, 5, 6, 7, 8. It is 8. Cool. And this one we have 7 zeros and a 1. Actually, opposite. 1 0 and 7 zeros. Or 1 1 and 7 zeros. And then we have 2 ones. And hopefully you're getting the pattern. 3 ones, 5 zeros, 4 ones, 5 ones, 6 ones, 7 ones, and 8 ones. Okay, so that's the only thing we can have. But if we have any 0, right, so if we stop the 1s, the rest of them are 0. So if the 1 stops here, we'd have the rest zeros. And all that's saying is how many zeros we have tells us how big our network is. Where our 1s are tells us what our network address is, right? And pretty soon I think we're going to get to ANDing. Anyways. Examining prefix length. So remember, prefix is when we have 1s and we write it as a /24. So we kind of talked about this, right? /24 just means that our subnet is a 255.255.255.0. Why? Because 3 255s is 24 bits. Anyways, you guys can look through there, but that's kind of what I was just talking about. Network addresses, host addresses, and broadcasts, right? So the network is everything contained, right? It's Clark. Then we have each one of these hosts, right? So network address just identifies where these hosts live. Then each host lives inside that network address. Then there's a broadcast to send to all of these hosts. And remember, so the network is the first number, right? So a lot of times it starts with 0, unless we start subnetting past the /24. Then our hosts are usually a number, right? They're a number in between the first and the last addresses of the network. And then for our broadcast is the last bit, or is the last address of a given network. So on this one, right, we take this number, we say, hey, where do our ones end? And our ones end right on this network. Then we take our zeros, and so this was a /24. So a /24 once again gives us 8 zeros, which equals 256. So the first one is the network. Alright, so 0 is our first bit that we can't use. So then we have to go 255 because we've used 1 there, and that would be our last host, so that's our broadcast. So that's how we would find that. So we can assign host addresses to anything in between 0 and 255. Hopefully this is making sense. If not, give it a good hard reading. Alright. First host, last host is what I'm talking about. Bitwise and AND operation. So the ANDing. So in ANDing, hopefully we've went over this, but 1, 1, and 1. So this is our network address, or this is an IP version 4 address. Then we see our subnet, just like we would in any subnet, right? So if we go into here, right, we go bang. Oh, well, I'm doing it. Don't have it statically set, so we say IP config, and we can see, we can even take this 169 that's not getting anything. But anyways, we go here. I don't know if you guys can see this, but what it's telling me is I have a 192, 168, a 1, we'll just say 1.10. And if I want to find, my subnet is 255.0. So what I'm going to do to find my network is I take 192 and break it into binary, which is 2 1s and 7 zeros. 1, or not 7, 5, okay, 6, sorry. 1, 2, 3, 4, 5. Need 1 more. Need 6 zeros. Okay. And then a 168 is that right there. 1, 2, 3, 4, 5, 6, 7. Oops, we need 1 more 0. I believe that's 168. And then a 1 is 7 zeros and a 1. Need 1 more 0. And then we have another 1. Alright, so then the subnet mask is a little easier, right? Because it's 255, so it's all 1s or 0s. So that's what we get there. So then our ANDing operation, what we do is if we have 2 1s, we go 1. If we have anything, if we have 2 0s, it's a 0. Sorry about that. That was a little difficult. If we have 2 zeros, it's a 0. And if we have 1 0 and a 0, it's a 0. Anything but 2 1s is a 0. So what ends up happening is we have this. And so what this is, then, is our network. See how it ends on the 1s? So it also tells us our network. So this is the AND operation is what tells us where a network starts and stops. So this is our network, and if we broke that back down into binary, it'd be back into dotted decimal, it'd be 192.1.0. Okay, and so the network for this is 192.168.1.0. I can take any IP version 4 address, and I can find out what the network is by ANDing it. Okay, so that's what. Let's get this back out here in front, and also we can see that basically anywhere we have 255s is going to say the same, right? So if we have all ones, that whole octet is going to say the same. But if we don't have all ones, then it will not. And we have to start breaking. We can actually break the networks into halves or quarters or eighths or 16ths or 32nds or 64ths or 128ths. Okay. And some networks we can't, but some networks we can. Alright, so lab using Windows calculator with network addresses. That'd be a good one to teach you how to easily find them, but make sure you can do the math yourself. Where are we? Okay, so now we're at assigning static IP version 6 addresses. So how do we do that? Well, we can go right to here, open Network and Sharing Center. We could also go to here and say Network and Sharing Center. Click it, open the same thing. Then we go to Change Adapter Settings. On Change Adapter Settings, we go into Properties. Bam. Then we go into Properties here. And I could set this statically. I'm going to keep mine at DHCP because, well, I don't want to interrupt my connection right now, right? Okay. Which, if I said it right, it wouldn't actually interrupt it, but I don't feel like it at this given second. So that's how we statically assign. Assigning an IP version 4 address dynamically. Well, as you guys just saw, go back into same place. And we say, and actually this isn't my network setting, so I can do whatever I want, but if we have it obtain automatically, it's going to use this thing called DHCP to pick up the address automatically, and makes our life so much easier. We love it. But until we get to DHCP and CCNA, we will be statically assigning IP addresses. But we can statically assign them there. Say we need an IP version 6. See this one that says Internet Protocol version 6? Bam, protocol, we can do it there too. Okay, so that's fun. Now, we have a unicast, broadcast, and multicast. Okay, so these are our 3 types of sending mechanisms we can use. So a broadcast is, we've talked about it. We send it to the last host on the network, and and there's limited and directed broadcast. So this is a limited broadcast that they're showing right here. So the limited broadcast means that we have all 255s in there. And so anytime we send to all 255s, it's a broadcast for whatever network we're in, right? Now we could do a directed broadcast, and a directed broadcast means that 255 can't go over to this network. But say this is the 172, I don't know, this is the 172, nope, I'm just going to go, I'm going to bring back up our notepad and do it that way. Okay, so, or we'll just do this one. Alright, so our broadcast, this is our first address. We can see we have 8 zeros, so we have 256 hosts, and we just use one with 0. So now we go to 255. 255 is our last host, so 255 plus the 0 I have here gives me my broadcast. So 192.168.1.255. If there was a network over here called the 1, we can send it and have it broadcast to each host on the network over here if this was the 192.168.1 network. Alright, but that's a little bit past where we are right now. But that's the difference between a limited in a directed broadcast. This is a limited broadcast, meaning 255, 255, 255, 255, where a directed actually has the network, and it can go, a limited can never go past a router interface. A directed actually can be routed to a different network. That's the difference between those. They're just do. So yep, that's what a broadcast does. And here's your directed and limited. If you guys are interested in that, take a nice little read there. I'd tell you all about it. Okay, so then we have multicast. And a multicast, did I skip unicast? I skipped unicast. So unicast just means one-to-one, right? He only sent it there. Remember, our broadcast sends it to everyone in the entire network. Okay, so one to all. And then a multicast is a one-to-many. So we just pick how many. It uses a special set of addresses, and it sends it to. See how it didn't send it to the router this time, so it picked most devices. And the only two that it actually going to accept it are these guys right here. So this is a multicast address right here. 224. Anything that starts with 224 is a multicast. We're going to be talking about that, I'm sure, in a few minutes. So another great thing about a multicast is it saves on bandwidth, okay? Because we can send one package and go to multiple devices. And so instead of having to unicast to here and then unicast in here, this uses half the bandwidth in this scenario. If we're sending a whole bunch of hosts, it would use a whole lot less bandwidth. So it's great. Some examples of multicast transmission are video and audio broadcasts, routing information exchanged by routed protocols, distribution of software, remote gaming, okay, because we have many people going to a server, so that server is probably going to multicast. Anyways, that's a multicast. You guys don't have to know a whole bunch about it. Do the activities, see what you think. Alright, so now, since figuring out routes and everything were very easy, now we're going to learn about private networks. So private networks, they're not routable on the internet. And so you'll notice that your home network isn't a private, or the ones I've been writing out. And so anything that's not these are routable on the internet and have to be registered, because they're public and they're how you get to a website, right? When you go to Google, you go to 8.8.8.8. And if you don't go there, I don't know, probably 8.8.4.4. Anyways, you won't see those in the private range. Okay, so there's different classes of IP addresses. The first class is called Class A, and we don't really use this anymore because we're once a classless. So Class A, I'm sure it's going to tell us this in a little bit, but they go from 0 to, I believe, 127, and then they actually go to 126, because 127 is your loop back, so it's actually registered to something else. But anyway, so 0 to 126.255, we'll say, is Class A. And Class A private address range is 10.0.0 to 10.255.255.255. That means you could use this network inside your internal network anywhere, right? Like these guys are doing down here. Then Class B is 128 to 191. 191 is actually registered for something else too. We'll just say it for now. All right, when we get to our classful assignments, and this is something you'll have to memorize, the addresses we can use for private is 172.16.0.0 to 172.31.255.255. Okay? Those are your ranges. Then finally we get to Class C, which is 192 to 223. And that is These are class C, and our range is 192.168.0.0 to 192.168.255.255, which this one is the most used for home networks. Anyways, so each one of these classes have a default subnet mask, and their default, a classful network, that's what it means. It has a default mask, and so class A have a /8 by default, class B have a 16, class C have a /24. So probably home users are used to 192 with a /24, which I hope you remember is 255, 255, 255.0. /16 would be 255, 255.0.0. And then a /8 you probably could figure out is just a 255 with three zeros. So basically, the further down the classes we go, the less hosts we have. So class A has the most hosts, class B has the second most hosts, class C has the least amount of hosts. How do we find those hosts? The subnet mask. And hopefully you're getting that. Okay. So you probably want to do this activity, and all it's going to ask you is, hey, is this a private or is it a public? So you start it. It says 132. It's going to pass to the internet. Why? Because it's not in a private range. All right. What's our next network? 172, 32. Oh, that's a pass, I believe. Oh, yep, because see, 31's where it stops. 172, 31. Oh, it's going to pass again. 123 is not in a private range. 179, going to pass again. Do any of them get stopped? 151, that's another passer. Come on, give me a private network here. This isn't really helping. Great job. It didn't even give me one private network. Alright. So, and how would I know it was a private network? Any number inside of there. Okay. Special use addresses. We kind of started talking about these. But, alright. So, the testnet is 192.0.2.0. Okay. So, the testnet, let's see, I don't really remember how to describe it. Set aside for teaching and learning purposes. These addresses are used in documentation and network examples. Unlike experimental addresses, network devices will accept these addresses in their configuration. You may often find these addresses used with domain names example.com or example.net. Alright, cool. So then we have a loopback. And so the loopback, what it does is it's in the 127. So it's 0.0, I believe. Let's see. 0.0 to I think it's to 255. Yep. So any one of 255, 255, 255. Okay. And so what the loopback is a computer pinging a virtual interface on itself to, if you ever are asked why would you ping the loopback, it's to test the IP stack, right? Because if you can't connect to yourself, you definitely can't connect to anybody else. So that's what the loopback is. Then we have this link local address, and you guys in IP version 4, it's a pain, right? Because the only time we see it, and it's this 169.254.0.0 to 169.254.255.255. The only time we see that is when we don't get DHCP. So DHCP failed, we couldn't find the server, so we get this, and it usually means we don't have network connectivity. That's not why, but it's just how it works. And so what it is just an automatic address, so that if no one could get network connectivity, we could still connect to these. If I said, hey, I'm 169.254, whatever, it's still in the same network, and we could go here. Or we could go here, but you're never going to be able to go to the network because it's link local. And so it's only from one side of the link to the other, not to this side of the switch, because the switch is a layer 2 device, so it doesn't care about these layer 3 addresses, but this computer does, this computer does, this computer does, and this router does. So we could actually manage all devices even with this 169. We just don't appreciate it that much in IP version 4 because we used to not know a whole lot about the addresses, or most people didn't, right? So when we see this, we get scared, but it just means usually DHCP isn't there, but we could still do stuff with it. Anyways, in IP version 6, we do a lot of stuff with link local. We've learned to appreciate the link local and use it for correct purposes. It's also called an APIPA address. They don't have a APIPA here though, but it's, I think, APIA, APIPA, which just means didn't get DHCP. Alright, so those are our special address ranges, right? Then the experimental is 240 to 255. That's for people like Cisco, and we're not going to worry about it. But this is actually a Class E network. Okay, so legacy classful. So this, we don't really use this, like I said. But anyways, Class A is what we have just talked about, right? And Class A 1 to 127, B 128 to 191, C 192 to 223. D, which these are multicast, so Class D is multicast, 224 to 239, and then that experimental. So you can go over that, but we've kind of talked about that up to here. But they're just classes, and they just mean, hey, our default subnet is this. This is the class it's in. So if you're in this number, you used to get this mask always. Then we do classless routing, so we don't care about that. But you're not going over classless routing yet, so we're not going to worry about it. So where do we register our public IP addresses? Well, with these associations like the INA and RIRs. And so regional internet registries, right? So the INA is Internet Assigned Number Authority, okay? And so then, in my understanding, we then break those up into regional internet registries, right? So we have a place for Africa, the AFRINIC, okay? APNIC, Asia Pacific, ARNI, American Registry for Internet Numbers, okay? So that one's important to us. LAC, NIC, RIPE, right? And CC. So anyways, so those registered numbers, and then these RIRs, assign them to ISPs, and ISPs are in tiers, and so we'll get there when we get there, I guess. But anyways, these ISPs register these numbers, and so each area, like Lewiston, how do we know an internet connection is coming from Lewiston? Because the public address it's registered to is registered to Lewiston and a cable one in Lewiston, and so that's how we know where IP addresses are coming from. So here's our ISP tiers. So tier 1, right? This is Sprint, AT&T. These are guys that span countries. They have internet in, say, Canada and the United States or worldwide. Okay, so huge Verizon, huge providers. Then tier 2 is like in a country, so we could say, or in large areas. So we could say like Cable One is in Arizona, Idaho, right? So they are large ISPs. They're probably a tier 2, considered tier 2. Then tier 3 is just a local. So there's stuff like Rodeo or First Step Internet, those kind of guys. Alright, do this public, private IP addresses. Okay, so IP version 4. The problem with IP version 4 is when we invented this IP version 4 thing, nobody ever thought the internet was going to blow up like it did. Nobody saw this coming, right? And so with IP version 4, we have IP addresses. We have 2 to the power of 32, right? We have 32 possible bits. Where the heck did my calculator go? Didn't even come up. Cool. Anyway, so 2 to the power of 32 is, I believe, 4.6 billion. Here, I'm going to try to get my calculator up one more time. Is it in the App Store? I have to download it or what? I don't know. It's popping up, but it's not going. We just aren't going to worry about it. So there's like only so many addresses we can have, and since every device needs an IP address nowadays, we tried NAT, and so NAT was actually, what it would do is it allows us to use these private networks and make the public networks separate out. So what it does is it translates your private network into a public network associated by your ISP, so we can have like 10 devices that translate into the same, and that's called network address translation. But it slows down speed, and well, it's fine. We'll use it for years, but it's not that great. Okay, 4.3 billion is our maximum addresses, right? So NAT kind of extended that out so we could have more than 4.3 devices, right? As long as you're on these private networks getting translated. But the Internet of Things was a branding. It's like, oh, we're going to put Internet on everything, right? And that's why I think the new one is Internet of Everything. So the Internet of Everything is like, hey, we're going to put network chips in to monitor shoes, right? Nike running shoes are going to be networked, and we're going to network trees so we can watch them grow. And so they need internet connectivity and all this. And so the plan for the future is we need a ton of network addresses. So we invented IP version 6, which is a 128-bit address instead of a 32-bit address, which this now gives us 340 unidecilent addresses, which is, I don't know if they say this there, but they'll say, oh, that's as many addresses as grains of sand in the Sahara Desert or something like that. Okay, so we invented IP version 6. And so since we have IP version 6 and IP version 4, network administrators are like tried and true guys. Like, they like cutting down on waste and all this stuff, but they love their IP version 4 and they don't want to learn about IP version 6. And so there's some ways to let IP version 4 work and with our current networks, but still use IP version 6 because they're handing out IP version 6 addresses for internet now. And so one way would be dual stack, and that's running both IP version 4 and IP version 6 at the same time. And this, if you ever get a question, what's the best way to do it? The answer will always be dual stack, right? Because IP version 4 is going to work, but we can still use IP version 6, so I don't know. It's our intro way in where we don't lose something we love. Okay, so our second way is tunneling, and this is probably the second most common way, the newer way. And so tunneling, what it does is it puts another layer 3 address on, and so what it does is it puts IP version 4 tag in, but then it goes to IP version 6. So we could tunnel either direction. This could be an IP version 4 network, and we tunnel IP version 6 to IP version 4. In this picture, we're tunneling IP version 6 over an IP version 4 network into an IP version 6, right? So what it does is it gives us another address and encapsulates an extra address, and so we have an extra layer 3 address on top of this, and so it thinks we're in here, but we have these two layer 3, and that's what makes it a tunnel. So this tunnel puts this on, and then it takes it off when it gets to its destination. And so this could be an IP version 4 address, and this would be IP version 6. Or in our drawing, this is IP version 6, and this is IP version 4. No. Yeah. So it goes across this IP version 4 network, and then this tag is taken off, and it's back in our IP version 6 network. It's very cool. Tunneling is awesome. Our final way is like how we were taking care of NAT, is this network address translation. So instead of, before we're taking a private IP version 4 address and translating it to a public, right? That's how most homes are running. This is doing it with, we're running an IP version 6 network, or we could run, again, we can inverse it. This could be IP version 4. But NAT 6 to 4 translates an IP version 6 address into an IP version 4 address. So at this router, it changes the source address, source IP address. If you think about your IP header, it changes the source address into an IP version 4 of probably this interface or of a range we've set, and vice versa. This IP version 4 gets converted to an IP version 6, so they can work together. And this is kind of frowned upon nowadays. So, IP version 6 numbers. So before, we didn't have to worry about this, right? Because IP version 6 decided, hey, we're going to use a hexadecimal system because we have a huge amount of bits. 128, right? Our old ones were 32, so 8 binary bits, no big deal. So this is our hex to decimal to binary conversion. Okay, so you can look at this chart, but hex goes from 0 to F, and this is its binary value in F, right? So hex is, each hex digit is 4 binary bits, so 2 to the power of 14, or 2 to the power of 4 is 16, because we have a value of 16. So usually hex, even though two hex digits are usually written together. Anyways, but that's where we get that. Each one of these letters, we have 16 options. That's why they are 4 binary bits. So, yeah. They're usually written like this. 0, 0. If you ever see a 0x in a number, probably with letters, it'll be in hexadecimal. Now we probably remember also hexadecimal, MAC addresses were in hexadecimal, so if you understood hex then, or didn't, now you can understand hex. But how we convert hex, right, is, so what we do is we say, oh, like this one, we have 8, 0. Okay, so in hexadecimal, 8 is 1 0, or 1 1 and 4 zeros, because so we wrote 8 out. Now we write 0 out, so we need 4 zeros because that's the equivalent in hex. Alright, and so then we can take this to binary and convert it to decimal. And so we know that this is 8 bits, and this is a 1, so it equals 128. So hopefully you will be asked to do that every once in a while, probably once on the CCNA and definitely on this chapter test. So make sure you can do that. So how is IP version 6 written? In hex with 4 digits. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. In 8 hextets. Okay, so each one is worth 16 bits. So 16, and our subnets we don't write out, we just do a prefix for them. So each one of these is worth 16, and then 16 times 8 is 128. Okay, so any one of these can be 0 through FFF, right? So we can have 2001. Now, we'll go to Notepad, just so it's easier to read. We can have 2001, something like this. 2001, a CAD, 0 dB, 8, 0, 0, 1, 0, 0, 1, 0, 0, 2, 0, 0, 3, and that's 4, and then we have 0, 0, 4. Okay, so that would be an IP version 6 address, but we have some rules in IP version 6 that we can do to make them easier to write. We can omit leading zeros. Okay, so we don't have to write leading zeros. So just by that, we could actually write this 2001, a CAD, DB8, 1, 1, 2, 3, 4. Okay, so that's an IP version 6 address. Now, let's say we had a similar number, except I'm going to copy this out, and where I had the ones, except for the first one, I'm going to put zeros. So, with what we just learned, we know that we can omit zeros. So we could have 2001 ACAD DB ACAD DB8 1 0 0 0 4. Okay, so that would be one way to write that. But there's another rule. Omit consecutive zeros. Okay? So we actually, and we do that with a double colon. So how we could do that is we could also write this same number as 2001 ACAD DB8 1 colon colon 4. That's the same address. Now we can only use the double colon once. So if we have two double colons, it's a invalid IP version 6 address. But we can do this. Anyways, you guys should hit this activity and practice those IP version 6 rules, because this is that's the most common question is this a valid IP address? And it's on the CCNA, or it's on the CCNA for sure. I don't know if it's on the CCNA. So you will have to do this sometime, but it's just omitting the zeros, and it's very simple. Okay. Now, IP version 6 changed a little bit. There's no longer a broadcast. There's unicast and multicast, and we have a special multicast in IP version 6 called an anycast, which is a one-to-many, which basically it does for servers, and it'll just go to the closest. It does a multicast, but whoever it hits first will send back and do it. The unicast is just one-to-one. The multicast is the same as multicast in IP version 6, except that it actually has a address range, which if we're doing link local addresses, it starts with, well, we're probably going to go to that. So anyways, so there's a defined unicast, and there's a defined multicast, and then we have these anycasts that kind of work like broadcasts. So our IP version 6, a /64 means we use the first 64 bits, and then the rest would be hosts. So our network would actually be on here, on this, our first 64 bits. If we did a /64 on this, right? So we have a /64. If each one of these octets is 16, we have 16, 32, 48, 64. So all of this has to be the same. So our network is 2001 ACAD DB8 1 colon colon /64. That would be our network address, and we still have that, but we don't have broadcast. So we have that. So anything that has 2001 DB8 ACAD, so anything with the same first 64 bits is going to be in the same network. So let's copy this. So our first network address would be colon colon 1, but we could have a colon colon, anything in the next 64 bits is a valid host, right? So 1.1.2.1. Wait, that's too many. No, it's not. Okay, so that's a valid host. It would be in the same network as, say, this. Those guys are in the same network if they're both in /64s, right? Because the first 64 bits just have to be the same, and the first 64 bits end right here, right? Because remember, these are 4 zeros. Oops, and that ruined my whole number. But oh well. Okay, so I hope you're getting that. If not, take a look at this one, and it should show you. We have a couple of different unicasts. So we have a global unicast, and the global unicast typically when we see it, it starts with a 2001, and we'll find out here when they tell us about our different types of addresses. Then we have a link local, and the link local starts with a FE80. So we often see FE80, and that's similar to the, I think it's FE80/7. But anyway, so anything address that starts with FE80 means link local. Okay, address that starts with 2001, and it could start with other things, but typically that's a global unicast, meaning it's like a public address. It can be it could be sent on to the, it could be routed on the internet. Then we have a site local, which is similar to a public, which is less likely, and it starts with FC. Then we have, what else? Our loopback. So remember that was the 127. It's just ::1. Loopback. And yeah, I guess they're calling this a unique local. It's called a unique or site local. I don't think it's very commonly used in IP version 6. At least not a lot of people are using IP version 6 like that. They're usually tunneling, but if you were, I doubt you'd do that. So anyways, this is going over link local, kind of like what I already said. So when you're assigned a link local address, you can go anywhere within side of one side of a network. Now you can't go past the router, right? These are different networks, so that's a different link. But we could go anywhere inside of here that the switch is connected to, right? Because switch is just a layer 2, so we could go to any layer 3 address inside of there, and that's the link local. The link local is also built automatically into every IP version 6, and if you guys want to go into CMD, IP, config, /all, you will find a link local on your devices. So like mine is, I don't know, where's my link local? Link local address, FE80, remember it said it started with FE80. 15C1 F5BD 8870 77EE, whatever, and then it's actually longer than that, right? It's 8, but it didn't work out. So anyways, that's my link local. You can make them shorter. Go in, right? If I want to set my link local, I could, right? Go to this one that's unplugged, go into my IP version 6 settings. How do I do that? Advanced? No. Well, there's a way to set it. Maybe there's not. I guess we could just use our link local. Like usually we set it in the router, which we'll be going over, and we set that as our default gateway because, I don't know, we always have a link local address. So structure, we have this, I don't know, all this is saying is typically in our /64, the first 48 bits, so /64 is pretty common. It's kind of like a /24, so the first 48 bits are global routing prefix. This is probably given, or this is given to us by our ISP, and these 16 are a VLAN. So these are the different networks. We could change the network in here, right? But this always stays the same if we want it routed. But we could be in here, we could go from 0 to F, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Then these are just host addresses and the next 64 bits. And so they just identify the host. So you can look at that. Interface ID is what they call it. But so, yeah, that's what we have going on there. How do we statically configure? Notice we never put in a subnet mask, we just put in a prefix, which we can go back, and I know we can set that, so we'll go back in, change adapter settings, properties, IP version 6, and we say, I don't know, 2001 ACAD DB8 1 colon colon 1 prefix 64, so /64. Then again, I would change probably my router link local to FE81, and that'd be my default gateway. Just set it like that, we're good to go. That's what's unique about IP version 6 is we can have one NIC can have both a global and a link locally. We have multiple networks on one network card, right? Then IP version 6 with this whole deal, we have different ways that we can dynamically assign. Remember, IP version 4 we just have DHCP, but we can actually use Slack, stateless address auto configuration. That's where the router ICMP actually sends a router solicitation, this thing, or the host asks for a router solicitation. They say, hey, I'm looking for a router, and the router does a router advertisement to these guys, giving them the prefix length, and the default gateway information. Okay, so we still need IP version 6, DHCP version 6, because just having a network address and having a prefix and having a default gateway, that means we could go to different networks, but we couldn't go to websites, right? We need DNS information. That's where the DHCP server comes in. So that's our second option of how we can automatically assign addresses with Slack and DHCP version 6. So the DHCP version 6 is going to give us DNS, the Slack's going to give us our network address and all that. Then finally, there's DHCP only, and that's where this computer would just go to here and say, hey, what's going on? How do I get this? And we'll learn more about this as we go through. We set flags on the router to tell it what kind of configuration we want to use. But I don't think they're going to ask you about it now. You can read this. This is, they're probably doing a stateless. Is that what they're doing? Okay, yeah, option 2. So this is what we call stateful addressing. So this is where it's getting both this and this, right? It's using both of these guys for information, and it tells you all about it in these down here. Yeah. So now we have this EUI64 process, right? Extended unique identifier or modified EUI64 process. This is a process of using client's 48 MAC address and inserts another 16 bits in the middle to create a 64 interface ID. So this is only to create the host portion. So remember, the first 64 are assigned by the router, by us, into the router, right? And so this is just it just shows us our device. So what it does is it splits the MAC, first 24 bits of the MAC address here, puts the other 24 bits here, and puts FFFE in. So 8 ones, and then 4 ones, and then 3 ones and a 0. Okay, it puts that in between them, and it makes the end of makes the last 64 bits of our host device, our host portion. So so IP version 6 addresses are assigned automatically. The reason they do this, right, is the minimum you have to have at least a link local address to run IP version 6. So that's what most people are running at home. You probably don't have anything more than an IP version 6 link local address, which, once again, we've been kind of talking about along the way, allows us to go inside of our own network but not outside of it. So static local addresses. Okay, this is actually important. I think this is on your test. To assign an IP version 6 address that isn't link local, well, so I guess they're just showing you link local right now. So we say IP version 6 address, and then FE80 space link local. We don't put a prefix on. And hopefully the next one is, nope, it's not. if we were doing an actual IP version 6 address, we'd do something like 2001 db8 a CAD and then slash, no space. It'd be something like this. We would do, that's the wrong window, I apologize. So we do something like 2001 db8 a CAD colon 1 colon 1 slash 64. And before that we put IPv6 to assign the address. Okay. To do that, we go into global configuration. Hopefully, you guys remember config T, So to get into our device, we say enable. Right, this would be a router. Enable it, and we say configure terminal, also known as config T. And then we go into the interface. We want to assign interface G00. And then this would take us into this prompt that says like config if, right? Whereas before this one would be conf, look like that when we're assigning it, and then this one would just look like this, and this one would look like this. So we go from user mode, user exec, to privilege exec, to global configuration, to specified configuration. And specified configuration, we're specifying the IP version 6 address for the G0, IP version 6, 2001 db8 a CAD 1 colon 1 slash 64, and then we press enter and it would put that address on there. And then we could do a similar action by saying, if we wanted to also set the IP version 4 for a dual stack, we'd say IP address. Oh, I forgot address up here, so make sure you guys don't forget address. And I would try this in Pack Tracer because this is actually going to be on your test, I believe, where you have to put in an IP version 6 address. So we'd say IP address 192.168.1.1. Then we'd say 255.255.255.0. Okay. Make sure you never, if you try to put in a network address here or a broadcast, it would say that's not valid. How does it know that? Subnet mask. We learned that today. Then we could go again. We could say, hey, I want to make this a link local address here too. So we'd say IP version 6 address FE80 colon 1 space link local. So that's the difference between link local and the other assigning it. But that's how we assign those 3 addresses to a router interface. Try that in Packet Tracer, please. It'll help you out a lot. How do you verify IP version 6? We can say show IP version 6 interface brief. Notice this is from privilege exec mode. We can do show IP version 6 route. This shows our routing table. Once again, from privilege exec, all of our show commands are going to go from there. We can ping ourselves from there. Go ahead, try those out on these commands, okay? Or on that command line there. Assigned multicast addresses. So basically, so if we see FF02 colon 1, this is all nodes. Okay, so this is link local nodes is what it's saying. So it sends, it says, hey, hello. Even though those are 2001, it's going to multicast to their link local. That's what the FF02 says. FF02 colon 2 is actually going to send a multicast to all routers on a segment from the host. So they're opposite directions, and so that's what those things are. Right, so these are router solicitations and router advertisements are getting sent through these multicasts. Okay. You guys can take a look at this. It's going to be pretty confusing right now. But anyways, that's what we're going to, I don't think you tested too much on that, so you'll be okay. No, but make sure you read through that, try to get a grasp on it. It's just how IP version 6 uses ICMP to assign messages. And so now it takes us to ICMP, okay? So what ICMP is ping, right? So what ping is doing is testing connectivity. There's no cache, there's no nothing. One time I had a CenturyLink guy tell me that a ping pool was cached, but actually what it's doing is testing connectivity. Can I get to this host or can I not? It doesn't tell me where it fails. We have another command where it tells me where it fails. It's called traceroute. So traceroute goes here, and then the time to limb says, hey, this is the last interface I was at. And then this is the last interface I was at. And I was successful. So traceroute tells us each layer 3 hop we have. So each time it's de-encapsulated and re-encapsulated, traceroute tells us that. Okay, so that's some things that traceroute tells us. Another thing we've learned about is router solicitation messages, router advertisement, neighbor solicitation. This is how, maybe you guys remember ARP. ARP is mapping layer 2 to layer 3. In IP version 6, instead of ARP, we use neighbor solicitation and neighbor advertisement. So that's how neighbors learn everybody on a network. Router solicitation is how we get that automatic addressing, and router advertisements is what actually does the advertising. So then the neighbor solicitation, we're building our table. We say, hey, I want to make sure that I don't have the same IP version 6 address as somebody else, which is called the duplicate address detection. Alright, and that's all done by ICMP version 6. So here's some ping stuff. You guys have been doing ping probably in class. If not, have a go at it. Also do the trace route, right, which will give you time to live. Trace route on a computer is different than trace route on a router. On a router or switch, we do trace RT, which is trace route. We actually type out trace route on a command prompt. All right. Also, ping stays the same on either, but yeah. So if you've never used ping, try doing the pinging packet tracer lab right here. And yeah, that was this chapter. It was a long one, so hopefully you had a good time with it. If you have any questions, please send me an email.